So today we're doing a paper chromatography lab. First we have the paper chromatography paper taped to a pen, and we have a 400 milliliter flask to hold it up.
We have a wet erase marker, a ruler to measure the distance of the color traveled, and 100 milliliter water. First, we're gonna draw a line a little bit above the bottom of the paper with the white erase marker, and then we're gonna pour the 100 milliliter water into the 400 milliliter beaker, and then we're gonna place this right above here so that we can watch the color travel and separate the wet erase marker. And then we're gonna take it out, let it dry a bit, and then measure it with our ruler.
Alright, so first we're gonna draw the line with the wet erase marker. Now we're gonna pour 100 milliliters of water into the 400 milliliter beaker.
Now we can place the paper over the beaker. Here's the walkthrough of our paper chromatography lab, where we separated the pigments found in a wet erase marker using tap water as a solvent. While the lab might seem simple, each step plays an important role based on core AP chemistry principles, especially intermolecular forces, polarity, solubility, and capillary action. The goal of paper chromatography is to separate a mixture based on how its components interact with the two phases. The stationary phase, which is the chromatography paper made of cellulose, a polar material that can form hydrogen bonds with polar molecules. The mobile phase, which was tap water, a polar solvent that rises up the paper through capillary action. Each ink pigment in the marker has its own chemical polarity and solubility, so they travel differently. More polar molecules stick to the paper and move more slowly, while less polar ones dissolve in the water and move faster. Let's go step by step and explain why we did each part of the procedure. Pouring 100 milliliters of tap water into a 400 milliliter beaker. We poured 100 milliliters of tap water to allow the paper to sit without touching the drawn line. Drawing a horizontal line with a wet erase marker. This ink line is the origin point, and it's where the pigment mixture starts. This step is crucial because it gives a baseline to measure how far each pigment travels. It needs to be shown above the water line so it doesn't dissolve instantly. Attaching the paper to a pen and hanging it vertically. This step ensures the paper hangs straight and vertical so the solvent moves evenly through the paper. Uneven positioning could cause skewed or distorted separation. Placing the bottom of the paper in water without submerging the line. By not letting the marker line touch the water directly, we allow the water to creep upward naturally through capillary action. This slow upward movement is critical. It pulls the pigment molecules with it, gradually allowing separation. Now let's break down what happens during the 30 minutes while the water moves through the paper. In the first 5 to 10 minutes, the water begins to move with the paper. At this point, capillary action starts pulling the water into the cellulose fibers. The ink begins to dissolve and we start to see a halo or slight smearing near the line. Polar pigments begin to interact with the paper, while non-polar ones begin moving. Between the 10 to 20 minute mark, the water continues to rise. The dissolved pigments begin separating more clearly. Those that are more soluble in water move farther. Those with stronger absorption to the paper slow down. The separation becomes more distinct. The water reaches close to the top and the different pigments have spread into clear zones of color. By the end, we see a visual representation of the ink's composition. Each color is a different chemical with different intermolecular interactions.
After 30 minutes, we removed the paper and made measurements. We found the distance the water traveled from the origin and the distance each pigment traveled from the origin. We calculated the RF values using the formula of pigment traveled over the water traveled. Each step in our experiment relates back to AP chemistry topics. For example, polarity and solubility. Molecules travel based on like dissolves like. More polar dyes stay near the origin, less polar dyes dissolve in water and move upward. IMFs. The stronger the IMF between pigment and paper, like hydrogen bonding, the less that pigment travels. Capillary action. Driven by adhesion, water sticking to paper, and cohesion, water sticking to itself. Chromatography principle. This method separates mixtures through partitioning between mobile and stationary phases.
The goal of this lab, once again, is to find the retention factor or how far each of the colors traveled and like how much it like distributed on the paper based on the amount of water that traveled. We can see all the colors, yellow, red, and blue. So what I'm going to do now is measure the distance that the water traveled from this, which is the baseline, up till here, and then I'm going to measure each color so that we can find out the retention factor. Here are the measurements for each color. So yellow is at 3 centimeters, and red goes all the way up to 4.5 centimeters, and blue is obviously 5 centimeters. And blue is also where the water stops.
This is how to calculate paper chromatography results using our example. We're going to look at the measurements from the chromatography test and figure out how far each color traveled compared to the water. Each calculation is the same. You take the distance the color traveled and divide it by the distance the water traveled. So we're comparing each color's movement to how far the water got. Let's start with yellow. It traveled 3 centimeters. The water traveled 5 centimeters. So we divide. 3 divided by 5. That gives us 0.6. Next, red. It went 4.5 centimeters. So we divide 4.5 by 5, and that equals 0.9. And finally, the blue. It traveled the full 5 centimeters, the same as the water. So that gives us a value of 1.0. These RF values show that the blue dye was the most soluble in water and had the least attraction to the paper, which is why it moved all the way with the solvent front. The red pigment was moderately soluble, while the yellow pigment had the lowest solubility or strongest interaction with the paper, causing it to move more slowly. This experiment demonstrates the Visa Marker ink is a mixture of multiple dyes, each with unique properties. Paper chromatography allowed us to separate and analyze these components based on their movement with the solvent, providing a practical way to study solubility and molecular interactions in the mixture. Thank you for watching.